This is the first video in a series of short videos that will cover our discrete math review for Foundations of Computer Science. The series covers some basic conceptual building blocks that we'll be using throughout this course. It follows the material introduced in the appendix of Ben Ari's Mathematical Logic for Computer Science. This slide set will span all the videos in the series, so we'll start with sets, sequences, and strings. That's this video. And we'll move on to operations on sets and strings. Then we'll do a video on relations and a video on functions. My assumption is that if you're watching this video, you have some familiarity already with sets, sequences, set operations, relations, and functions. I'm not assuming any prior knowledge with strings. I will cover those from the beginning. So if you're following along and you're finding that lots of things that we're counting as review are really new for you, that is okay, but please do make sure you reach out so we can get you caught up. Okay, so without further ado, let's move on to the actual content of this video, which is about sets, sequences, and strings. And we will start with sets. So what is a set? We have a definition and some notation. We define a set as a collection of elements, and we use the symbol epsilon here to express set membership. So this is read as A is in S, and it just means that A is an element of the set S. Likewise, the negated epsilon is read as A is not in S, and this just means A is not an element of the set S. Again, you've probably seen this before. The cardinality of the set S is denoted by these vertical bars, and that just means the number of elements that the set contains. We have a symbol for the empty set, and this represents a set that has no elements in it, and therefore its cardinality is 0. So that takes care of some very basic terms and notation, and we'll talk next about how you can actually define a set. So there's 3 ways we're going to talk about where you can define a set. The first is the explicit way. This is the simplest. You just write out the elements and say what it equals. So you say S, for example, is a set that's equal to the colors red, yellow, and green, or R is equal to the numbers 1, 2, and 3. And this works fine for finite sets. Obviously, it does not work as well for infinite sets because you cannot write them. So for infinite sets, we need another strategy, and this is often called set comprehension. Some textbooks say abstraction. And in this technique, we define a rule that says what kinds of elements that we allow in our set. So what you can see here is we've defined a rule that we say we're going to let all elements n such that, that's how the bar is read, so n such that n is an element of the integers, that's what z stands for, and n is greater than or equal to 0. So this is our rule for saying that some element can enter our set, and we're saying this is equal to n, and what that means is that it turns out that this set definition is equivalent to defining the natural numbers. Another example, our set E here, we said all elements n such that n is an element of the natural numbers, and n mod 2 is equal to 0. So this is going to be defined as our set E, and it turns out that this is equal to the even natural numbers. And then, mostly for completeness, I'll add a third way of defining sets, and this is through operations on sets that have already been defined. So for example, to give a very simple example, we have the set K here, which is equal to the union of S and R, which we've given in our examples above, and so it contains the elements red, green, yellow, 1, 2, and 3. We haven't defined union yet, but again, I'm assuming you're familiar with it. We will talk more about different types of operations that you can use with sets and strings in a later video, so you can look forward to that. So sets, what do we use them for? They are the basis for a number of things that are going to come up repeatedly in this course. The first is relations, the second is functions, another one is equivalence classes, and another one is partial orders. And we're going to see all of these again quite soon. Finally, just in case you haven't seen these in a while, there are a number of infinite sets that are important enough to get their own special notations. We usually use the blackboard bold capital N to denote the natural numbers. And similarly, the capital Z is for the integers, Q is for the rationals, R is for the real numbers, and C is for the complex numbers. So that concludes our very short review of sets. We will now move on to sequences. And I'm not going to spend too much time on sequences. I'm introducing them mostly because we need them as part of the definition of strings and Cartesian products, both of which are going to be much more important to us, especially strings. Okay, so here is the definition as given in Ben-Ari. I'm going to read through it and then we'll talk about what it means. So we have some set S, and we can now define a finite sequence F as a function from a set containing the elements 0 through n-1 to S. Right? So this is a function that goes from this set back to this initial set S that we assumed. So this is a bit of a strange definition when you first see it, I think, particularly because we have not said what n is, and we have this set that is defined from 0 up to n-1. It contains all the elements, all the numbers from 0 to n-1. So the idea is we have a finite sequence, and since it's finite, there is some number n, which represents the length of the sequence. And if we take all of the numbers from 0 up to n-1 and put them in a set, what we have is essentially the domain of a function. Right? These are inputs of this function, and the outputs are going to be some elements in S. And those outputs, or the range of this function, is going to be a finite sequence. An infinite sequence is the same thing. We use a very similar definition, but instead of this finite set that goes up to n-1, we just use the natural numbers as our domain. So hopefully that makes sense, and you may have to think about it for a minute or pause the video and draw it out, but I hope that that explanation is actually intuitive and corresponds to what you would expect when you are writing a sequence. The main idea is in a sequence we have some ordering of elements, and they have a position and a value, right? And so all we're saying is we're using the domain to indicate their position, and whatever they are in S, that is the value. So assuming you have some sequence, we can say we have some sequence F on the set S, and the sequence is denoted as S sub 0, S sub 1, S sub 2. These are the elements of the sequence in order, and it's written in parentheses. That's what distinguishes it from a set, which will be written in brackets. And we say where S sub I is equal to F of I. So again, what's happening here is F we're thinking of as a function. Its domain is the natural numbers, and we're plugging in natural numbers, and that's what I represents here, and getting elements of S, which have this index, right? That's what the same on both sides is, that I. So for example, we're plugging in 0, and our function F is giving us S sub 0 as the output. We plug in 1, we get S sub 1 as the output. So this gives us both the ordering and the value of the elements in the sequence. Finally, just another bit of terminology. We can call a finite sequence of length n an n-tuple. So as I said previously, this is pretty much all of the time we're going to spend on sequences in this entire course, but I do think it's useful to work through this definition and make sure you understand it. We're going to have many other definitions like this. So next we'll be moving on to strings, but I do want to add one more note, which is that if you're paying very close attention, you might say, wait a minute, you're defining sequences here in terms of functions, but we haven't defined functions yet. And this would be a good point. And actually, when we go on to see functions and the way they're defined, you'll see there's actually a bit of disturbing circularity to the way this is all set up that occurs in Ben-Ari's index. What I'll say about it is, again, this is just a review, and we're being a little bit hand wavy here. If we were going to do a whole course on set theory, we would spend more time developing foundations very carefully to avoid this kind of circularity. But for right now, we're just kind of refreshing your memory, and I'm assuming right now that you know what a function is enough to understand this definition, and then when we get to the actual definitions of functions, we'll clarify a little bit, but this is not meant to be some sort of airtight construction of these mathematical objects. Okay, so now lastly, we'll introduce an object that, as I mentioned previously, may be new, and this is a string. It's something that is of great importance in our work in Foundations of Computer Science. And in order to define it, we first have to define an alphabet. But this is a very simple definition. We define an alphabet just as any finite set. So for example, the set containing the numbers from 0 through 9 and the set containing the numbers 0 and 1 are both alphabets. Likewise, a set containing just the letters A and B is an alphabet. And you can tell from the definition that it's actually much more flexible than what we're using it for right here. And this tends to be the case, right? We could define all kinds of weird alphabets because there's lots of finite sets, but typically for our purposes, we can stick with alphabets that look a lot like the alphabets. They look like the characters that we expect in our strings, whether we're working in binary or in decimal, or we're just using A's and B's to sort of represent an abstract binary alphabet. In terms of notation, we usually use a capital letter sigma to denote an arbitrary alphabet, and we call the elements of sigma letters or symbols. So now with this definition of alphabet and our definition of sequence, we can go on to define a string. So we define a string over sigma as any finite length sequence of elements of sigma. Right, so for example, if sigma is the set AB, then AA, BAB is a string of length 5 over sigma. The length of the string x is denoted by these vertical bars, much like cardinality. And so you'll need to know from context whether x is a set or a string. If it's a set, then that would mean it's cardinality. If it's a string, then it means its length. Finally, there's a unique string of length 0 that we define over any alphabet sigma, or every alphabet sigma, and that's called the empty string. And we denote it by this lowercase epsilon. So you'll notice we're now using epsilon for two different things. And again, it's useful to understand through context which one we're talking about. However, we do use usually a sort of stylized larger epsilon when we're talking about set inclusion, and this is just a regular lowercase epsilon, denotes the empty string. Okay, so an important note before we wrap up is that we have sort of three different things here that all kind of look like they represent nothing, and it's important to keep them separate, right? So we have the empty set, we have a set containing the empty string, and we have the empty string itself. And just keep in your mind that these are three different things, right? And try to work through how they're different. So first, the empty set is a set that has no elements in it, right? So remember, its cardinality is 0. A set containing the empty string is a set with one element in it, and that element is the empty string, right? Even though it's empty, it's still a thing. And so this set has cardinality 1, right? So this set is not the same as the set on the line above. Right? Finally, the empty string itself, remember, is not a set. It is a string, and so it doesn't have a cardinality at all. That's one way to think about it. Instead, it has a length, and its length is 0. But it is not the same as the empty set. So just kind of keep those things in mind and practice thinking of them as separate entities to reduce confusion when you encounter them later. So that concludes our first video in the Discrete Math Review series. I hope it was helpful. In the next video, we'll move on to the section Operations on Sets and Strings.